Hello, and welcome back to the course on Physics for Engineers. We are still on Chapter 14, the chapter on electromagnetism. So before we proceed with this lesson, let us first review some concepts. So in the previous lesson, we have discussed about magnetic flux. When we discussed about the Gauss law for magnetism. So the magnetic flux, similar with the electric flux, is the closed integral of the field that with the Gaussian surface, dA. So A here is our Gaussian surface. Now, for magnetostatics, since it's always a dipole, a pair of a north and a south pole, then the total flux, so the total closed integral of B dot dA is always zero, which means that the magnetic field lines that flows into the Gaussian surface is the same or equal to the magnetic field lines that flows out of the surface. So unlike electricity, wherein you can have a single positive charge or single negative charge, in magnetism, there's no single north pole or single south pole. It's always a pair of a north and south pole. So we have also discussed about currents, resistance, and EMF. And they are all related by this equation called Ohm's law. So for an ideal source of EMF, the EMF is just equal to the voltage, which is just equal to the current times resistance. So for this lesson, the second lesson for this chapter, we will be talking about two laws involved in electromagnetic induction, and these are Faraday's law and Lenz's law. So in the early 1800s, induction experiments were carried out separately in the UK and in the US. And Michael Faraday carried out induction experiments in the UK and Joseph Henry in the US. And they both describe electromagnetic induction. So when you move a magnet with respect to a coil, an induced EMF is generated or is generated in the coil whenever there's a relative motion between the magnet and the coil. So they have found out that an induced current and an induced EMF, and there is an induced current and induced EMF in the coil if the coil moves with respect to the magnet or the magnet moves with respect to the coil. So, or another thing that they have found out is if the area of the coil changes. If the area of the coil suddenly increases or decreases, then there's also an induced EMF, an induced current. So basically, when you move the magnet with respect to the coil, you're actually changing the magnetic field. And you change the area of the coil, so you change the area of the coil. And those two factors, the magnetic field and the area, corresponds to the magnetic flux. So if you will recall, magnetic flux is B dot dA, magnetic field times the area. So whenever the flux changes, it's either the magnetic field changes or the area changes, or both magnetic field and the area changes. So whenever there's a magnetic flux change in magnetic flux, then there will be an induced current and induced EMF in the coil. And the induced EMF depends on the number of turns of your coil and the change in magnetic flux with respect to time. And this is what we call Faraday's law. So this quantifies how much induced EMF is in the coil. So this is change in magnetic flux. So if we substitute the equation for the magnetic flux, which is just the integral of B dot dA or B dA cosine phi. So you will notice that there are actually three factors that affects the change in that can change when the magnetic flux changes. It's either the magnetic field will change with respect to time, or the area of the coil change with respect to time, or the angle between the magnetic field and the area vector changes with respect to time. So Faraday's law states that the induced EMF in a closed loop equals the negative time rate of change of magnetic flux through the loop. So there's a negative. The negative sign here is very important, and I will explain that later. So if you will recall, basically the flux is just another word for flow, but take note that we are this is a static field, magnetostatic na field. So basically, the magnetic field is actually not flowing. So I'm just gonna put that in quotation mark. So basically, flow. But take note, the magnetic field is actually not flowing through a surface. So when the magnetic field and the area vector, take note, the area vector is always perpendicular to the surface of the area, are in the same direction, then that will actually give you the maximum flux. So when theta is equal to 0. So when theta is equal to 0, cosine 0 is 1. That's the maximum flux. Whenever they have an angle, then you have this equation B dA cosine phi. So B dot A. And there's 0 flux whenever the area vector and the magnetic field is perpendicular to each other. Because when theta is 90 degrees, and the angle between the area vector and the magnetic field is 90 degrees, and cosine 90 is 0. So there's no flux whenever your area vector or your magnetic field and magnetic field are perpendicular to each other. Meaning, the magnetic field is parallel to the surface. So that's what that means. Okay. So Faraday's law equation is actually equivalent to this one, the closed integral of E dot dl. And basically, this electric field here is what we call the induced electric field. So the induced electric field is the reason why there is an induced EMF and induced current in the coil. So if you will notice in this example, you have another coil with a changing current, di dt. And then this is your AC ammeter, or in general called a in old terms, galvanometer. This is just an ammeter, your AC ammeter. And then you will notice that if the current is changing with respect to time, then there will be an induced electric field in this case. So the induced electric field has the same direction as the induced current and the induced EMF. So the induced electric field is the reason why there is an induced EMF and induced current in the first place. So take note, the electric field is the one creating the voltage, creating the EMF, and the EMF is the one pushing the charges to flow within the material. So this is the example that we have discussed in the previous lesson, wherein if you have an alternating current, a current that's changing with time, then it will have an induced electric field in this region or in this coil, in the clamp, and an induced electric field will generate an induced EMF and induced current. So the induced electric field actually curls around the induced magnetic field and vice versa. So same direction as the induced current. So in this case, this is the induced current, and this will be the direction of the electric field also. So it's curling around the induced magnetic field. So in this case, this is the magnetic field of this wire, and the induced magnetic field is actually in the opposite directions. I will discuss about how to determine the direction of the induced magnetic field in the next slides. So the second law associated with electromagnetic induction is Lenzs Law. And Lenzs Law is all about the direction of the electromagnetic induction effect or phenomenon. So Lenzs Law states that the direction of any magnetic induction effect is such as to oppose the cause of the effect. So that is actually the negative sign in Faraday's law. The negative sign means it's opposite. If you have a negative, it's opposite. It's opposite to oppose the cause of the effect. So for example, you have an increasing magnetic field in that direction. So therefore, there will be an induced magnetic field in the opposite direction to counteract, to oppose the increase in magnetic field. And if the magnetic direction of the induced magnetic field is downwards, then the direction of the induced EMF and induced current is in this direction. So take note, right-hand rule. The thumb is the direction of your induced magnetic field, and your fingers are the direction of your induced current and induced EMF. So this is a phenomenon, a natural phenomenon. Nature doesn't want any changes in magnetic flux. That's why if the magnetic flux changes, there will always be a counter effect, and that is the electromagnetic induction effect. There will always be an induced EMF, or sometimes we also call that a back EMF. whenever there is a change in magnetic flux. So that's nature. Nature doesn't want changes in flux. So in this example, we have 4 examples here. So in the first example, you have a magnet, and this is the north pole of the magnet. So meaning the direction of the magnetic field is downwards. And in this case, you are actually moving the magnet towards the loop. So meaning if the magnetic field is getting closer to the loop, the magnetic field is actually increasing and in the downwards direction. So meaning there's an induced EMF in the upwards direction, and this is the direction of your induced current. So if you reverse, so for instance, this is now the south pole, and you move the magnet away from the loop, meaning the magnetic field is decreasing. And the direction of magnetic field, since this is south pole, then the magnetic field direction is towards the south pole, and the magnetic field is decreasing. So meaning, if it's directed upwards, but the magnetic field is directed upwards and it's decreasing, so therefore, there will be an induced EMF to counteract the decrease in magnetic field. So the induced EMF is still upwards in this case. Now, in another example, this is the north pole and of the magnet, so meaning the direction of the magnetic field is downwards, and then you move the magnet away from the coil. So this means that the direction of the magnetic field is downwards and it's decreasing. So therefore, you need to have an induced magnetic field in the same direction to balance the decrease. So if it's increasing, the induced EMF and induced magnetic field is actually usually in the opposite direction. But if it's decreasing, the induced magnetic field is in the same direction. Okay, so in order to solve problems in electromagnetic induction, we use Faraday's law to solve for the value, and for the direction, we use Lenzs Law. So let's have this example. So you have a magnetic field between the poles of the electromagnet shown here, and this is the magnetic field. It's from the north pole. So these are 2 circular magnets. So there's a north pole here and a south pole here. So the direction of the magnetic field is upward, and it's actually increasing at a rate of 0.020 Tesla per second. So the area of the loop is given 120 centimeters squared, or that is equivalent to 0.0112 meters squared. So you always convert your units to square meters. And the total resistance of the loop is 5 ohms. So find the magnitude of the induced EMF and the induced current in the circuit. And letter B, if the loop is replaced by one made of an insulator, what effect does this have on the induced EMF and induced current? So let's first solve for letter A. So for letter A, the induced EMF is just Faraday's law. So this is Faraday's law. So since there's only one loop, so n is equal to 1, and integral d dt, derivative of integral of b dA cosine phi. Now, the area vector and the magnetic field here is in the same direction, meaning theta is 0. So cosine 0 is 1. So you just have integral of b dA. Now, the magnetic field at every point in the area, in the surface area of the loop, is actually the same. So meaning, you can take b out of the integral, and then the integral of dA is basically just the total area. Integral of dA is just A. So the total area A, which is given, this one. So we now have 2 terms in our derivative. Now, since the area of the loop is fixed, so we can take it out of the derivative. So the remaining term here in the derivative will now be just the magnetic field, dB dt. So our induced EMF in this case is basically just negative A dB dt. So A is given, and dB dt is also given. It's 0.020 Tesla per second. So magnetic field per unit time, the change in magnetic field. So using this, we have obtained a value of negative 0.0024 volts, or negative 0.24 millivolts. So you move the decimal places the decimal to 3 places, and you get millivolt. Or you multiply by 1000 to get millivolts, from volts to millivolts. So the negative sign here implies that the direction of the induced magnetic field is opposite the direction of the changing magnetic field. So usually if you get a negative EMF, that means the direction of the induced EMF is in the opposite direction as the changing magnetic field. So meaning the induced magnetic field in this case is downwards. And the direction of the current, induced current and induced EMF is in that direction. So downwards, so meaning this is the direction of my induced current. So that one. Okay. So we now have find the induced EMF. So to solve for the induced current, we just take the use Ohm's law. So current is EMF over R, or voltage times resistance. So we just take the magnitude of the EMF to take the magnitude of the current, and we get the resistance is 5 ohms. So you have 0.0024 volts over 5 ohms, and that is volt over ohms is the unit called ampere. And you have 0.0048 ampere or 0.048 milliamperes. So that's for letter A. That's the induced EMF and the induced current. Now, for letter B, suppose you replace this loop by one made of an insulator. An insulator is not a conductor. It's plastic, glass, rubber. Those are insulators. Insulators means they resist the flow of charges, or they resist current flow. So, if you replace your loop with an insulator, it's no longer a conductor, then what will happen is there will be no current. So, no induced current, but there will still be an induced EMF. There will still be a negative 0.24 millivolts of EMF. But since the resistance of an insulator is very, very large, so negative 0.24 over a very large value, so that's the property of insulators, the resistance is infinitely large, very, very large. Then, any number over a very large number is approximately 0. So that's the reason why current don't flow on insulators, on rubbers, on plastic, on glass. It's because of their resistance. They have a very high resistance. Okay. So let's have another example. So in this example, we have coil, a circular coil or circular loops. There's actually 500 of them, but in the picture you can, there's actually 500 circular loops. And this is basically a loop that is on side view. So if this is your loop, it's actually on a side view here. So you place 500 circular loops with radius 4 centimeters. So this is the radius, 4 centimeters of this circular loop between the poles of a large electromagnet, and where the magnetic field is uniform. So there's a uniform magnetic field and at an angle of 60 degrees with the plane of the coil. Now, the field decreases at a rate of 0.200 Tesla per second. So the field is uniform, but the value is decreasing. So when I say uniform, meaning the magnetic field at this point and at this point and at this point is all the same. It's the same at all times. That's what being uniform means. It's different from constant. Uniform means at all points in this region, the magnetic field is the same. That's what being uniform is. But the magnetic field value is decreasing at a rate of 0.200 Tesla per second. So what are the magnitude and direction of the induced EMF? Okay. So from here we can deduce. So since the magnetic field is in this direction and it's decreasing, meaning to counteract the decrease in magnetic field, there will be an induced electric field in the same direction to counteract the decrease, to oppose the decrease. So that's the direction of our induced EMF, induced magnetic field. Therefore, if this is the direction of the induced magnetic field, then the induced current and induced EMF and induced electric field in the loop will be in this direction. So meaning current will flow out of this point. It will curl around and enter this point and then move upward. Okay. So we use Faraday's law. So this is Faraday's law. So N is 500. And then since the magnetic field is the same at all points in the area of the loop, and the angle is constant, so we can take it out of the integral. So integral of dA is just the total area A. So we have B cosine phi A. And then cosine phi and A doesn't depend with time. They have no derivative with respect to time. So you can take it out of the derivative. And we have negative N A cosine phi dB dt. Okay. Then substitute the values. N is 500. The area is, this is a circular loop, so pi r squared. So pi times the radius in meters. So convert 4 centimeter to meter, that is 0.04 meters squared. Cosine of the angle between the magnetic field and the area vector. So take note, the 60 degrees given here is not the angle between the magnetic field and the area vector. Because the angle between the magnetic field and the area vector is actually 30 degrees. Take note of that. 60 degrees is just the angle that the loop makes with the magnetic field, not the area of the loop. You need to take the angle between the area vector and the magnetic field. And the area vector is always perpendicular, 90 degrees, with respect to the surface of the loop. And here, dB dt, the change in magnetic field, when you say decreasing at a rate of 0.200 Tesla per second, meaning that's negative. The value of the magnetic field is subtracted by negative 0.200 Tesla every second because it's decreasing, a decreasing magnetic field. So when you, the word here, the keyword here is decreasing, and that corresponds to this negative sign here. So there's a negative sign here, there's a negative sign here, and you get a positive value, positive 0.44 volts. So the positive sign again implies that the direction of the induced magnetic field is in the same direction as the changing magnetic field, so which is this direction. So that is the magnitude, and the direction of the induced EMF is in this direction. It's out of the page here and then into the page here. Okay. So last example. So this is a simple alternator or AC generator. Alternator is another term for AC generator. So an alternator is a device that generates alternating EMF. So what is the induced EMF at any time when the coil is rotating at a constant angular frequency omega? So we start with our Faraday's law. Now, the magnetic field here is constant, and the area of the loop is also constant. So you will just have something like this, B A cosine phi. Now, the magnetic field doesn't change with time. The area doesn't change with time. What changes with time is actually the phi, the angle between the magnetic field and the area vector, because this loop is actually rotating. So the angle between the magnetic field and the area vector, so when the loop rotates, the area vector also rotates, and the angle between the magnetic field and the area vector is also changing. So here, if you will recall your chapter on rotational kinematics, so the final angular position is just equal to the initial angular position plus omega t plus 1/2 alpha, the angular acceleration, t squared. Now, in this case, we will assume that the initial angle is 0. And since it's constant angular frequency, then therefore there is no angular acceleration. So your your phi is just omega times t, angular frequency times time. So you take b and a here out of the derivative, and so you will have cosine of omega t. The derivative of cosine omega t is basically just negative sine omega t, and then derivative of omega t with respect to t is omega. So you have omega here and then sine omega t. So the negative sign is gone because the derivative of cosine is negative sine. So that is now the induced EMF in an AC generator or a simple alternator. You will notice that it is time dependent. It depends on time. Depending on t, the value of the EMF changes. So so that's what we call alternating, an alternating EMF and alternating current. So this is actually what happens to the EMF. So the EMF is actually alternating. So from, for example, our EMF or voltage in our homes is 220 volts. And that's actually the root mean squared value. But the real value actually rotates from a positive value to 0 to a negative value to 0 to a positive value. So it's actually sinusoidal. It's actually changing, alternating. So this is actually an alternating voltage, and the current that it produces or generates is an alternating current. So a commercial alternator uses many loops of wire wound around a barrel-like structure called an armature. And the armature and wire remain stationary while electromagnets rotate on a shaft. So not shown here. So this is actually the armature. So in a turbine, such as in power plants, in waterfalls, hydroelectric power plants, or windmills, it's actually the electromagnets that are rotating with respect to the coil. The coil is constant. The coil is fixed. It's not rotating, but the magnets are actually the one rotating with respect to the coil. And again, electromagnetic induction is just a relative motion between a coil and a magnet. So it's either the magnet with respect to the coil, the magnet rotates with respect to the coil, or the coil rotates with respect to a magnet. So, and that's the end of the lesson on Faraday's law and Lenz's law. So those two laws are very important in describing electromagnetic induction. So that's the end of this lesson, and I will see you again in the next lesson for the chapter on electromagnetism. So bye-bye.